Hi, in this video we are going to talk about spanning trees again, but instead of considering classical algorithm and the lazy implementation of the Prim-Zjarnik algorithm, we are going to talk about the eager implementation of the Prim-Zjarnik algorithm. So basically, the aim is the same. We want to construct a minimum spanning tree. But the lazy version of the Prim-Zjarnik algorithm is that we use a priority queue or a heap in order to get the minimum edge weights. Plus, we insert all the edges to the heap without modifying the content. That's why it is called lazy, because we don't care about the content of the heap, we don't update the content of the heap, we are lazy. What about the eager version? We do update the content of the heap if necessary. And basically on every iteration we have to check whether is it necessary to change the content of the heap, because there may be several cases when there is already a shorter path to the spanning tree, and that's why we have to update the content of the priority queue accordingly. Okay, so let's consider this situation. We have 7 vertices and several undirected edges with given edge weights. We can start our algorithm at a random vertex, for example the vertex E. It's very important that we are going to iterate our algorithm until we consider all the vertices. We have been talking about that the classical algorithm is an edge-based algorithm. The Prim-Zjarnik algorithm, on the other hand, is going to run until we considered all the vertices and we include all the vertices in the minimum spanning trees. Because for a minimum spanning trees, not all the edges are included, but all the vertices are included. Okay. So basically it is the same as for the lazy algorithm, that we keep visiting all the neighbors of this vertex E, the vertex B, the vertex D, the vertex F and the vertex G. And basically we are going to construct a heap and going to put these edges to the heap. So the edge between E and D, the edge between E and F, E and G and E and B. Then we are going to get the minimum edge, so the edge with the minimum edge weight. It's going to be the edge between the vertex E and the vertex D. So we are going to visit this vertex and we are going to consider these vertices and this edge between the two vertices to be done, in the sense that we are not going to bother about them anymore. Okay, then we keep visiting the neighbors of D. And from now on, it's going to be different from the lazy implementation. So what about the D-F connection? We know that there is a cheaper path to the F node, because we know for certain that going directly from the E vertex, it's going to cost 4. But going from the vertex D, it's going to cost 5. So we exclude the D-F edge as an option in the spanning tree. So I'm going to mark it as red. Okay, so what about the DC connection? Is it the first time we consider the vertex C, so we add this DC edge to the heap because it may be good? Okay, so that's why we push the DC with the edge weight 6 to the heap. What about the DA connection? It is the first time we consider the vertex A, so we add the DA edge to the heap. Okay, we add it to the heap. What about the DB connection? We have considered a path to vertex B so far from vertex E. The total cost from vertex E is 7 because the edge weight is 7. But the cost from vertex D to vertex B is 4. So that's why it is cheaper to go from vertex D to vertex B than going from vertex E to vertex B. So that's why we are going to exclude the EB as a solution, because it's not the shortest path in the sense that it is not the cheapest solution. So we update the heap and we get rid of the EB edge, and basically we add the DB edge instead with the cost 4. Okay, then we iterate as far as we haven't included all the vertices in the spanning tree, so we iterate until all the vertices are green. So we get the item from the heap, it's going to return the edge with the minimum edge weight. It is the 4. Okay, as you can see, there are two edges with weight 4, we can choose between them at random. For example, I'm going to choose the EF edge. So we visit the F and we consider it to be the part of the minimum spanning tree with the EF edge. And of course we remove the EF from the heap. Then we visit all the neighbors for the vertex F, the C and the G. And we pose the question that what about the FC connection? We have considered a path to vertex C so far from the vertex D. The cost from vertex D to vertex C is 6. The cost from vertex F to vertex C is 3. It is a better solution, so that's why we are going to exclude the DC edge from the minimum spanning tree, because there's a better solution. So we are going to eliminate it from the heap, and we are going to insert the FC edge instead with edge weight 3. Okay, then what about the FG connection? We have considered the path to vertex G so far from vertex E. The cost from vertex E is 9. The cost from vertex F to vertex G is just 2. So what does it mean? It means that we can make sure that this EG edge is not going to be part of the minimum spanning tree, because there's a better solution. What is this better solution? Basically going from F to G. Okay, so we get rid of, and basically we insert the FG edge with the edge weight 2. Okay, then we keep going because we haven't visited all the vertices in the graph. So we get the edge from the heap and it's going to return the one with the minimum edge weight. It's going to be the edge between the F and the G, so we include the vertex and the edge in the minimum spanning tree. We remove it from the heap and we visit all the unvisited neighbors of G. It is the B, so what about the GB connection? We have considered the path to vertex B so far from vertex D, and the cost from vertex D to vertex B is 4. The cost from vertex G to vertex B is 8. So that's why the GB edge will not be part of the minimum spanning tree. Okay, so we keep going because we haven't visited all the vertices in the graph. So we get the minimum edge from the heap. It is the FC with the edge weight 3. So we keep visiting them and include them in the minimum spanning tree. Of course, we remove it from the heap and going to visit all the unvisited neighbors for C. What about the CA connection? We have considered the path to vertex A so far from the vertex D. The cost from vertex D to vertex A is 12. The cost from vertex C to vertex A is just 2. What does it mean? That we have to update the heap. And we can get rid of the DA connection because it is very, very expensive. So we get rid of this connection in the heap and basically we are going to insert the CA connection with edge weight 2. Then we keep going because we haven't visited all the vertices. So we get another item from the heap. It's going to return the edge with the minimum weight, which is the CA connection. So we are going to include it in the minimum spanning tree. Okay, we remove the CA from the heap and visit all the neighbors of A. What about the AB connection? We have considered the path to vertex B so far from vertex D. The cost from vertex D to vertex B is 4. The cost from vertex A to vertex B is 1, so we update the heap. We can come to the conclusion that the DB edge is not going to be part in the minimum spanning tree. We are going to delete it from the heap and going to insert the AB connection instead with edge weight 1. Of course, we keep going because again, we haven't finished yet. We haven't visited all the vertices in the graph. So we get the item from the heap, which is going to return the AB connection. And basically with this, we are done. We have visited all the vertices in the graph. So we have managed to include all the vertices in the minimum spanning tree, so the algorithm terminates. The overall cost basically is the sum of the distinct edges, which is going to add up to 14. So we can come to the conclusion that with the help of the eager Prim-Zjarnik algorithm, we are able to construct the minimum spending tree with overall cost 14. So what's the main difference between the lazy and the eager implementation of the Prim-Zjarnik algorithm? That for lazy implementation, we don't bother about the heap. We just keep inserting the edges and we keep getting the edge with the minimum weight. Okay, of course in the code we will see that we have to check whether we have visited the given vertices or not, because again we have to avoid including cycles in the minimum spending trees. It's very important because we are going to talk about the applications, we are going to talk about the spending tree protocol, and basically the aim of the spending tree protocol is to avoid cycles in the local area network. So it is the same that we are not able to include edges that's going to form a cycle. So the eager implementation of the Prim-Zjarnik algorithm is going to take care about the content of the heap. We are going to check whether is there a shorter path to the spanning tree, and if there is, then we update the content of the heap accordingly. And basically it is working fine, as you can see. So that's all about the eager implementation. Thanks for watching.